complex solutions that include some of those pieces. And then we also do your more standard penetration testing and red teaming and other things like that. A little bit out of scope for this talk, though. So we've been working on servers in particular for a couple of different customers that have unique and interesting use cases and design requirements and drivers that push security in the right direction. So it's been fun to learn sort of over time about where the vulnerabilities have been and where the problems have been, and then seeing it evolve and seeing the attack surface shrink and a bunch of other sort of more maturity-minded things that have been occurring, and working through that. So this talk then, firmware cartography, right? Well, what does that even mean? What are we talking about? So the point here is we're saying in a modern new server, attack surface has been reduced, if configured correctly, attack surface has been reduced to such a degree that we're left with much smaller windows through which we need to do all the stuff we want to do as attackers. In doing so, how do you figure that out, right? And that's the whole point of this talk. It's saying, let's pull apart the whole sort of server, a modern server. We want to talk about it in terms of this is how we approach the problem. So there are a lot of talks, across Black Hat this year and in prior years that focus in on a lot of the individual pieces. We're going to use a couple of case studies here in a bit that we'll talk through that. But the idea here is to explain and cover the attack surface, the reasons why you would want to hit these different things, the kind of problems that exist in these different components. And as we get towards the end, we'll particularly focus on this is where it's going, right? So if you care about security, then you're doing X, Y, and Z, and you are configuring your newer servers in certain fashions. Even when it's fully configured, you end up with certain amounts of attack surface. And so that's where we enjoy spending a lot of our time. Right? A modern server now, it's full of many different components, right? You've got servers inside servers, you've got computers inside computers all the way down. As I mentioned, there's been a lot of talks over the last 15 years, new UEFI, BMC, there's constantly new pieces. But as it becomes more hardened, that attack surface is concentrated into fewer and fewer components. You end up where you have gating events where you need to compromise that thing over there first to get all the information that you might want to crowbar open the attack surface again, and then be able to pivot into other components. So we'll talk through all those different areas. All right. So what's the stuff that matters here, right? So we're being a little hand wavy on purpose, and we are summarizing multiple components into one group to be able to talk about it in those fashions. So like here's what we've got, right? We've got host, SMM, BMC, peripherals, and chipset, and we'll walk through those here in some detail. So like starting in the host, this is the thing everybody thinks of. This is it's exactly what it sounds like, right? This is your software that's running on a CPU. For a lot of the attack chains that we'll talk about today, we kind of gloss over what happens inside the host, right? Like there's a ton of talks talking about all, and you guys know all the. Compromise. There are some implications that we'll talk about in maybe a little bit later too. But some of those implications that we're talking about today is vulnerabilities that are related to these platforms in user land on these hosts, and that's actually a gigantic attack surface. So it's relatively unhardened. Like I was looking at it in prep for this talk like last week. And think I found two ODAs like just fell out on my lap. I think it's a very unreviewed environment, and this stuff is meant to tear down all the walls that we're saying are important, right? So like we really like isolation. We really like pulling apart components and minimizing the amount of interactions that they can have, so that you have a sort of a choke point. You can look at that. You can make sure that the code that's processing between these interfaces has been hardened, it's been reviewed, et cetera. Whereas a lot of the systems management types of software, enterprise pieces that get layered on for any vendor, doesn't matter, for any OS actually too. So whether we're talking about Windows or Linux or anything else, it's designed to create as many pipes as possible between these different components. So I just mentioned that, and that there are definitely security ramifications to it. And what it also means is that some of the vulnerabilities that we find, that we use ourselves in testing, being able to get a greater viewpoint on a system to be able to assess it. It's been a little while since I've heard the argument, but there used to be a common argument of, well, you have to have root to do that, right? Or those kind of things. And one, getting root's actually not that hard, that said. But then even on top of that too, there are several cases where these enterprise management layers are exposing that functionality down to user land and down in unsafe ways. So the issues that just fell on my lap were related to how well that's secured and who can interact with those things. So
the other thing to keep in mind is that for the host, you're not always running on your own hardware. So now with the cloud and bare metal hosting, there are times when you're going to be running on a machine that's not yours, and you're going to be giving your machine out to someone who's not you. So in that case, you're explicitly giving access to the host. So it's another sort of twist on the old the attack model that we have in mind, where here we're giving up the host, keeping in mind that we have these other gates, hopefully keeping the hordes out.
Yeah, and I know that Windows in particular has been trying to focus on some of this level of hardening and trying to turn off some of the interfaces that would let you do these things. It's certainly at least easily, right? A lot of the stuff on Windows, it's configured in extremely hardened fashions and would often require you to have kernel level execution to be able to get the access you needed. It's a lot easier to do on Linux on a normal, say just a new install. You go and download one and install it. It's a lot easier. The other thing about hosts, the other thing that's interesting with this too is that you end up where, I guess the way we view this problem statement is that, as I just said, in a lot of ways we assume compromise of the host, and it would be our recommendation that everyone assume compromise of the host, right? Your security designs and the way that you configure these systems should be in such a way that you assume that if it's doing anything, that all of our computers do today, there are avenues to get the level of code execution that you need to then be able to trigger and reach into all the stuff we're going to talk about here. And so I know of environments that will have multiple, server configurations, kind of depending on risk level. That makes a lot of sense, and I'm in support of that. But you have to accurately weigh what the sort of likelihood of attack is or successful compromise of that server, right? And so for different servers, it could be in different use cases. Like if this particular server is sitting in the DMZ and it's running, something awful, and so we think it very well could get compromised. So we isolate it differently than we do one on the internal network, for example. But it's worth rethinking that and looking at what are those use cases that I'm underappreciating the danger level, right? Because one of I guess the starting point from this whole talk is it's from the standpoint of when you're starting, or when you consider what the attack surface of a host like this is. If you care about these things, there is a huge amount you can do to reduce the threats, to reduce the vulnerability of a given host. And this is focusing on the pieces that are left over. If you don't care about those things and you don't configure it, attempting to reduce attack surface and attempting to lock it down, then there's almost no barriers at all. It's extremely easy to pivot through to all these different components. And even in the newer stuff, like for years and years, people beat up on Supermicro because they didn't do any firmware signing at all of their BMCs and things like that. And they started implementing that in the last few years. And so like that's one example of some of that maturing. But even so, allowing in-band management with all of that offers in any sort of a situation where an attacker can get on that host is really bad. So, okay. So switching gears a little bit, right? So first thing, host. Also, this is where for most threat models we talk about that where most of our attack chains kind of start from compromise there. What that also means is that for a lot of this, what we're talking about is attack surface that's exposed to the host. And so that's primarily where we focus. That's where we usually start from. And then as we begin to compromise other components, then you get different viewpoints into the system, and then you can begin to explore the vulnerability of those other sides. And so that said, we're starting from there, and then we'll work through all these different components and sort of the pros and cons of them. But and then I guess wherever we're starting from a different place, we'll call that out. Okay. So system management mode, really like there's entire talks just about every one of these components. So we're obviously not going to that level of depth. For what matters here, all we're really saying is that it's another place that attacks can be launched from. It is becoming, over time, is becoming more and more of the centralized location for certain types of secrets. So it is not a secure enclave, like it's not a TPM, it's not this hardware-backed secrets, a safe place to keep your secrets. And so there's implications to using it that way, but it is still an improvement. So what's happening is that over time, where like in years past, maybe everything was accessible, now we're finding different ways to turn those off. So perhaps the attack surface that used to be there all the time, now that attack surface is only there during boot and only when it boots into a certain mode. So like, if you've updated your UEFI on your laptop or anything in the last while, like all the recent systems, the way that works is differently than it used to, and it's observable to you as the user. Like it writes to a location, and then it sets some flags, and then it triggers a reboot. And then when it's coming back up, right, it takes a different path, and then it can actually unlock the flash that it needs to unlock, and it can do these updates. Well, so that's sort of changed. That's one of the things that's changed. We've had several others as well, like where there were these different buses that were accessible that are now not accessible at all, except for these time windows, or in some cases, and what are our two sort of case studies that we'll go into detail here in a bit, what they're focusing on is these areas where it was attack surface that used to be open. Now we've closed it off, and we've tried to figure out how can we make it so that SMM can still talk to it, but nobody else can. And so there's a few places where that really matters. Like Intel chipset has some attack surface there that is shut down after boot, except they still need SMM to be able to make certain types of queries against it. In-band management is another common one. That's our other example that we'll give here too, where it was an interface that used to be on all the time. If you want to turn it off, you can now, except maybe you can't always turn it off. And so this is that corner case and like how they implemented that solution. And then other use cases, right? Like you talk to anyone who's trying to design one of these, or like a large cloud provider that's trying to architect a server that would be resilient against these kind of problems. You can't just shut everything off because there are so many components inside a server now, so many flashable components that may need updates. Something could be broken. So like you can't. I mean, there would be physical ways you could like never allow something to be updated again and make it truly read-only. But you can't actually do that in the real world, right? So you have to have methods to use some of these privileged buses and privileged interfaces, but we've got to figure out how to do it safely. And so there have been some interesting neat ways that I've seen that done. And so that's part of what we're talking through. But it's a hard problem to solve because some of those things have to be enabled. And if there is a pathway that can be used, then a lot of what our job is trying to figure out how to crowbar that back open, like I said earlier. SMM can be attacked from a number of places. Like the most common ones are hosts. The SMI interface is still problematic. There've been a lot of talks about that, and they're all better than this one at covering it. Go read those. There's a lot of interaction between the BMC and SMM. So SMM is often sending requests out to the BMC and then processing those responses. It also is reading data and things out of out of storage in locations, either EFI variables or data stored in flash, other things that the BMC can also influence. So there are there are paths from once you get root inside the BMC, being able to poison responses that are coming back in and then gain code execution at a higher level. Generally, you don't need to do that here. Like in that the SMI interface is large enough, usually, that you can find the vulnerabilities that you need on that side. And then peripherals are really interesting. So one, like as Dion and I have processed this whole domain and been trying to figure out how do we take all of this giant amount of work that's been done and that we understand about the sort of the modern threat, vectors for these systems, how do we boil that down to what really matters? And this is one of the areas that I think is the most interesting. It's the most interesting to me right now. That these other components that they are not always present. So we're not talking about like, Intel chipset stuff or the BMC or these other components that are sort of always on the motherboard. These are components that are used in either specific use cases, like a particular motherboard has this feature to it or whatever, and then that's exposed through some bus, but it's its own processor, has all of its own resources. Or we're talking about, components that are plugged into a PCIe slot, right? And both sides of that are really interesting. The attack vectors into those devices is pretty fascinating. Like oftentimes it's really simple and it's not all that like fancy. I mean, it's, you call the firmware update function and then you update the firmware on the peripheral. But it's not always. Sometimes it can be getting very complex on that side too, of reaching into the device. But then once you're on the device, the attack surface exposed to you as you're coming back up from the peripheral is also fascinating. And there's like a lot of different examples or different ways that compromised compromised peripheral can get back into SMM and the host itself. All right, so BMC, right? Again, lots of other talks on this, so I'll try to gloss over it quickly. If you're not familiar with what it is, it's an entire Linux system that's sitting there on your motherboard. It's asynchronous in that it's like it has its own state. It can be turned on or off while the host can be turned on or off. It allows for it's useful for persistence, right? I mean, it has all of its own resources. It has all of that. There's been a lot of talks talking about that and different methods for doing so. And then useful for reattacking the host, right? Getting back in. It has a lot of attack surface to the host. It also has a lot of attack surface to the management network. This is one that has been talked about, been mentioned several times. I don't feel like at least the public exploitation or like the red teaming world doesn't really use it. We probably should. We probably should use it more. Like the pivot from the host to the BMC is not hard. And once you're on the BMC in highly restrictive environments, I mean, so maybe that's a question for you, like to think about, are you filtering requests coming out of the BMC? And like, where can those requests go? Assume that if someone can compromise a BMC, assume they can compromise all the BMCs if they can talk to it. So like, we can do a lot at the network layer to restrict the ability to, to come out of one BMC and then take over all the other ones. But you should assume that like if you're sitting on the BMC, then that means you know all the secrets. Like the whatever the passwords are for IPMI, and you obviously have vulnerabilities in the BMC, you know how to trigger them. So like if there's not network layer controls on the traffic coming out of that, then you can pivot and laterally move across very large segments. Like I know in places that do it, like you either end up where nobody works to restrict it at all, and so they're just on the network just like any other node, and okay, it's not really that special. But in a highly restrictive environment, you'll have management networks that are all plugged into this. And they're isolated, and you can't get on those networks normally. But if you do get on those networks, you can get to everything. Like all of the barriers all go away. All right, so talking about peripherals again a little bit more specifically, right? This is a broad category for what we're talking about here. So this does include like anything that is off. It's off host. It's not any of the components that we're talking about. We're kind of like lumping them all together here. We'll talk about ESIO and as a use case here in a minute. We kind of categorize that as a peripheral. Obviously, and then anything that plugs in anywhere. If it has a cord that plugs in or it's a card that plugs in, it counts. The one unique thing about their attack surface is that they have varying, attack surface. Like different components will have wildly different attack surface. So you've got, I saw the write-up on the Qualcomm chain of bugs, like just this week, where, there was another talk last year that was the first time I'd ever seen someone do it, I think. But coming in and popping the Wi-Fi sock itself, so like a little tiny ARM chip inside the Wi-Fi card, and then being able to pivot from that back into the host. That's the same attack surface that that we're describing here. It's just a little bit of a different vector. And so like there was another one, someone did that to chain all the way through for Qualcomm just this week. And it's getting harder, especially on those types of devices where they now are having, like I think I saw it has ASLR and it has some containerization of some sort, like it's some isolation. So it requires multiple chains to get back through. But you want to do that for all the same reasons that they do. Like you would want to do that on a server, all the same reasons that they did that on the Qualcomm chipset. Oh, and I guess, yeah, so the other one to that too is we didn't really think about what the attack surface is for VMs either. So think about like your VMware farms that you've got for, like there's a bunch of different use cases where you would want to expose some of this either directly and on purpose, or it's exposed indirectly, but no one's really looked at it yet. So the attack surface of peripherals, I think, is still not well understood or well researched. I'm particularly interested in some of the translation that occurs. Like there are, across all the different VM solutions, all of them in some fashion are you're either directly plugging one of these things in, you're mapping it in, or it's translating requests for you in some fashion. And I know that I know of multiple scenarios where normal transactions are also what's used for administrative functionality. So like think about a drive and how do you update the firmware on the drive? Well, in some cases you use different SCSI commands. Well, like how tight are all of the proxies of those SCSI commands actually in real life? Like, is it really terminating the request and then making a new one? Is it abstracting it somehow? Or is it a straight pipe? And in what situations? And it can get really complex really fast. So that's kind of why we don't really know a lot about some of that attack surface. But it's certainly worthwhile to look at. And as we move forward, it's interesting to me because it's one of the things that will still be there, right? Like you're going to have performance reasons why you're going to want to slave hardware directly into your guest in some cases. And then even from that, like you're going to constantly have other peripherals that you need to allow some level of access to that's hardware on the outside. So we're not finding them with our standard sort of fuzzing frameworks and these things we're looking at today, where we fuzz emulated devices a lot. But I don't know that we're good at being able to predict how something will be decapsulated all the way down in the hardware on the other end. All right. And then lastly, category of just this is the catch-all for all things chipset, right? So everything, like all the Intel stuff and the AMD stuff, we're talking the PCH, SPS, all of those pieces. It's for the server side is a little bit different from the normal consumer line. So like, I'll say it's behind. So the newest features will come out on the user side first, and then at some point they will move over onto SPS. So like we're talking about like CSME versus SPS and some of those types of differences. But the like the architecture for SPS, one of these days it's going to change. I don't think it has yet. I haven't looked at it in a little bit. Someone from Intel probably is in here and will tell me. But that attack surface is there. There have been several great talks about it. I'll say it is due to the changes that have been happening in the last couple of years too. It is time consuming for RE and exploitation. We've done it a couple times. We've looked at it. We've written we've POC'd vulnerabilities that we found that have various primitives that are useful in these spaces. But it's not well understood. Although that is changing. I know there was a talk on CSME here yesterday that covered a lot of the architecture that they're using now, which is great. That's wonderful. Like using modern, compiler defenses and all those kind of things. That's what we want to see. And it'll be fun to see that sort of like standardize and get pushed into the server lines as well. It does have attack surface right across those things. We're not going to really talk about chipset very much in here, in that it is an area of continued research and motion right now. So, all right, you want to take over on this part?
So now we've kind of given an overview of our whole map. We understand the components in the system. The next step is to sort of drill down a little further. But before we do that, we should talk a little bit about, quickly, how we think about the trend right now and where we think things are going and where it will be useful to look for more bugs and for sort of twisted attack surface. We've said it a few times, maybe 5 or 6. Modern servers they're complex. There's a bunch of components. They're connected together, much more like a network than anything else. And they're only now starting to be treated as networks with complex routing and filtering. And as we said when we talked a little bit about the host, cloud and virtualization changes these things in ways that the designers of them probably didn't anticipate. And because of that, our attack surface has changed. And we're having to backport, like I said, these filters, these ways of ensuring that components are correctly isolated. These are things that we never anticipated, or we still have in the servers a lot of these protocols that date back to ISA buses and things like that. So clearly, we're not moving quickly here to come up with the latest designs to ensure that we can do this filtering. Instead, what we're trying to do is ensure that we can find fixes in the meantime before we can, the hardware can catch up to the way we think about threats these days. The alternative, of course, is to defeature things. And we're seeing that. So we've seen customers remove entire physical connections that are usually not there, that are usually there. And we've seen people very aggressively defeaturing UEFI firmware to ensure that things like software SMIs are missing, are no longer, are not so prevalent, much less attack surface. And sort of as I mentioned before, what we really want to do is try and find a way to secure these components using the hardware that we have, using the systems that we have, to ensure that we have some measure of security until we get to the point where we can design our perfect system. And one of the things we see going forward is this using the SMM as a sort of like a secure enclave. As Nathan mentioned earlier, it's not a TPM, it's not trust zone. It has a lot of the problems that you'd imagine. And because it wasn't treated like that, although there are some chipset features that allow you to, for example, ensure that the flash can only be written during SMM and certain pins can only be used during SMM, it's becoming more useful in terms of software protections. Like I said, the backporting these security features to the existing system. And we're seeing a lot of that. So the upcoming, what we'll talk about next, after a short sort of detour, will be the deep dive into some of these components that have ported a filter or control into SMM, into the UEFI, such that it controls the traffic between the host and some of these other components. As I said, the trust placed in SMM has changed over time. So originally, if you wanted to update firmware, you would be able to do it without rebooting, right? You would just ask SMM through a software SMI to enable the writes to the flash, and then flash your new firmware. As SMM became less of a boundary, we ended up using more of these features that Intel provides, such as the protection registers and things like that will not allow you to. These are set once during boot, and then you have to reboot to clear them again. So as you come up, you set these protection registers, and now flash can no longer be turned back on to be writable. So to do the firmware update, you have to reboot and do this early in boot. So you're not doing it at the time that the OS actually has attack surface to the SMM. maybe, hopefully, we'll see a little bit of this, the tide turning. Some of the UEFI defenses now are actually ending up in firmware. So things that have been around for 2 years or so in, as example code, as provided code from vendors are making it into firmware. Things like actual page tables in SMM, protections provided to ring 0 outside of SMM from SMM. So ensuring that SMM can't write to pages that are that you wouldn't want it to. Again, it kind of all follows this trend of ensuring that all these components have well-defined boundaries and that it is more of a network than a sort of cooperating system nowadays. And you need to ensure that these components have their own boundaries and their own security controls. As we said again in the very beginning, we're trying to hit this from the host. We want to think as an attacker starting at the host. We gave all the reasons why we think we can get there, and sometimes we're even provided that access from the person that is defending against us. And coming at this without this knowledge 2 years ago, it was hard to find all of these things. It's a complex system. There's tons of acronyms. We've tried to define as many as we could without getting crazy. But I'm sure that anyone else starting here, looking for service and looking for vulnerabilities, assessing the security of a motherboard, a modern server, will have to go through the same trials that we have. And I think, hopefully, I'll provide you a quick laundry list of things that you can go Google later that might help you. Like I said, things we wish we knew 2 years ago. First, you hear all these things, and if you've been doing software development long enough or security long enough, you may have touched upon them. But the main ways in which you're going to talk to these devices, these other components from the host, are going to be memory mapped I/O, port I/O, or through a controller, through the I2T or through LPC, which is also going to be this port I/O. So these are the main interfaces that we need to monitor for if we want to reverse engineer any of the systems that we're trying to assess. So dynamic tooling. ChipSec is sort of the catch-all. It provides you with the ability to, first of all, it has a bunch of modules that will do these dynamic tests for you. So you can run its suite of tests against it. It's at various levels of update depending on how new of a set of a CPU or chipset that you're using, PCH that you're using. But it is a great base, and it gets updated fairly quickly. So that would be my first Google. As far as enumeration goes, getting a lay of the land from the PCI bus would be really useful, and it'll tell you what components you can talk to there, which buses you're going to be able to speak to from the host, and how you're going to be able to speak to them. DMID code is going to parse the SMBIOS, the ACPI stuff that is provided from BIOS to the operating system to be able to configure this and to be able to know what peripherals are available for you to test. You're not always going to have an accurate view of this, and this is also not ground truth, right? DMID code is only what has been provided to you as an attacker. I2C probe is another tool that will allow you to sort of scan an I2C bus for anything that will respond. Again, it's not perfect, and it's using heuristics to try and do this, but it may help provide you some sort of ground truth or some things to follow up on. The last piece is the one that I think we found most useful, is creating tools that allow you to inspect the traffic that goes along these interfaces. The first set are tools like straight debugging of things like firmware update tools, and then dynamic binary instrumentation tools like Intel Pin and Valgrind. What those will provide you, and the types of tools that we've written to use those, are tracing mapping of MMIO for these various PCI devices. So if you have one device that you're targeting, you can create a tool that will trace all open system calls, looking for an opening of dev-mem, because oftentimes these firmware update tools are trying to run without any use of the driver. And so they'll map dev-mem in, they'll map the bar register from PCI, and then they'll do straight MMIO register access to poke in exactly what they need for their firmware update. And if you can trace those, you can get a great sort of map of what they're trying to do. It's very similar to how you would approach reverse engineering a network protocol. So you would take Wireshark, you'd run Wireshark or TCP dump, you'd fiddle a little bit, and then you'd go look at the traffic. This is exactly the same approach. For reverse engineering things like drivers that are doing these, I mentioned like the user space flash updated or firmware update tools. Sometimes you'll want to look at the behavior that you're not aware of or you don't understand in the kernel. And to do that, we've used a tool called Ply, and we were told about this cool tool called MMIO Trace, which does exactly what I described, but for the kernel, for a kernel module versus user space. The last thing is this subhook tool, which is it allows you to build a shared object that can be injected prior to the user space tool running and do exactly what I described for like the DBI for Intel Pin and Valgrind. But it's really quick. It's really nice. You should check it out. Static tooling, I'm going to blow through this pretty quick, so we're running out of time here. IDA, of course, to look at the things that, anything that's running on the system. We use it for EFI, UEFI modules. We use it for the tools that are running in user space for doing firmware flash updates, firmware updates. And we use it for reverse engineering firmware if we can get it. So some of these components will have firmware running on their microprocessors, and we can use IDA to reverse engineer those. There's a number of plugins that allow you that provide you the ability to mark it up with EFI things, EFI information prior to looking at it, because it's EFI requires a lot of data flow. A lot of things are dynamically looked up. We wrote a bunch of tools in Binary Ninja that do some of the same things. And then UEFI tool is a great tool for extracting all of the UEFI modules from a firmware blob. We use Kaitai structs to parse some of these, because oftentimes we'll have firmware that is not in the like ELF or something that we can load. So sometimes we'll need to either pull the firmware that is embedded in something like a flash update tool, a firmware update tool, to pull it out to then put in these other tools. And of course, grep. Some general tools, general tips. As I said, oftentimes we're looking at firmware updates, and the reason for that is that these firmware update tools are often going to do things beyond just firmware update. They're going to be used in the field to do things like pull debug information to, they may embed other tools that you want to understand, that'll explain more about the peripheral or the system that you're using. And then, of course, Intel PCH data sheets are publicly available, unlike some other data sheets, and provide a lot of information. We talked about the firmware update tools. UEFI modules are similar. Oftentimes, there'll be things in SMM that are trying to talk to the component that you're interested in. So they're important to look at. And I think the last one is going to be, if you're looking to pivot from the host to SMM, we tend to look for things like a SMRAM read first or a BMC root first. The reasoning is that both will provide a lot of information to us about how the firmware in SMM is running. If we're curious about the configuration and we can't understand it from the existing image. BMC root will allow us to do things like kernel and logging, other very useful things. Okay, let's get into a deep dive. This is, we talked a little bit about the components. We talked about why we think they're important. Gave you a 100-mile-an-hour overview of all the tools that we use. So let's look at one specific interface, the interface between the host and the BMC. The host and the BMC interface, there's this IPMI document, a specification that describes these interfaces. And the one that we're concerned with is going to be called the system interface. IPMI defines it and then defines a bunch of ways that a system can expose this interface. There are 4 that they give in the spec: KCS, SMIC, BT, and SSIF. In all of my travels, I've only seen KCS and SSIF used. KCS is, I'm not going to get into the details. You can read the spec if you really are curious. But the main takeaway is that KCS is going to use the LPC bus or eSPI bus to expose a very simple sort of byte-by-byte serial interface to the BMC. SSIF is very similar, but it uses the I2C bus instead. So if we're on a server and we're curious what interface it has, one of the things we talked about was this DMI decode command. If you run DMI decode, one of the things that are often advertised is the IPMI device. And in this example, we have a KCS, an exposed or advertised KCS device, and the base address is going to be that CC0 IO port. The Linux kernel provides a driver, so you can talk to the IPMI. You can talk IPMI to your BMC. And once you mod probe that or insmod that, the dmessage output will help you understand whether or not that what you saw in the DMI decode is actually accurate. Because like I said before, sometimes DMI decode is not accurate. When it works, it tells, it's going to, especially these last two lines, it's going to say that it found the new BMC and that the KCS interface is initialized. Oftentimes it will be disabled. And if it's disabled, you won't get those last two lines and none of your IPMI tool commands will work. So why would you want to disable it? Well, going back to this, these system interfaces are not meant to be used, or at least this boundary between the host and the BMC through these system interfaces is not meant to be privileged. So it was unauthenticated. If you're going to talk to the BMC through these interfaces, you're assumed to be able, it's assumed that you're allowed to, and that the system designed it that way, and that it was configured in such a way that they wanted you to do this. So what do we do about that? This KCS interface is unauthenticated. A thing we haven't talked about is that this interface and these IPMI commands are often going to provide a huge amount of surface, but beyond that, they're also going to provide features that allow you to do things like flash the BMC. So if you want to prevent, if you don't want to trust the host, and you want to ensure that the host is not allowed to just flash the BMC whenever it wants, what can you do? Well, you don't want it, right? So just get rid of it. We'll just throw it out. We'll defeature it. Unfortunately, there isn't just one. So we saw that advertisement of one in the DMI decode output, but often there's going to be more than one. There's going to be two or three. Why do we need multiple KCS interfaces? Why would a BMC ever support multiple? It's only going to be plugged into one bus. So well, why does it have more? Well, what we found out is that the SMM might need to access the BMC to do things like send a log message about a fatal hardware error or a significant hardware error. And so here we have, again, this is the IPMI spec showing that they have all these sensor reading errors that the SMM can provide, can send over to the BMC that an administrator can then go look for, saying, why is my, why does it turn off every 20 minutes? Oh, it's having a thermal problem. Okay, fine. So why don't we just turn off the one interface and leave the one for SMM, right? We have these two interfaces. One is exposed to the OS. One is meant to be used by SMM. Well, we'll just turn off the OS one. Unfortunately, it's not that easy because, like I said, KCS works over this port IO, and the chipset wasn't designed to prevent access from port IO across these things. You'd have to, one approach would be to reconfigure your entire LPC controller setup every time you enter and exit SMM. Not a great approach, slow and messy. So it's not simple. Do we give up logging serious hardware errors? Well, we could, right? And we've seen people approach this in that way. You can turn it off. You can do it. More often, we've seen the approach of an ostrich with his head in the sand. So oftentimes we'll see people just turn it, just ignore it. Ignore it as a problem and assume that because it's not exposed via the DMI decode, via the SM BIOS metadata, we won't deal with it. Nobody will find it. It'll be fine. That one I'm not a big fan of. The other one, the second one, is this Amazon Nitro security chip. So AWS gave a talk in 2018 at the 2018 reInvent discussing their new Nitro architecture. And one of about a third of the middle of the talk was talking about this Nitro security chip. And they mentioned that they have this filter that they put in, this hardware filter that ensures that no non-volatile memory is ever written. And they call out, in fact, the BMC interface, saying that they need to lock that down. So if you're not Amazon and you can't create your own hardware, what can you do? Back to this idea of using SMM. Lenovo took this, developed this KCS lock feature. So this code is in BIOS, and when UFI when SMM is triggering the ready to lock event or on ready to lock, this callback is going to get called, and what this does is it sends this. It generates a random nonce, this 32-bit random value, and it sends it across to the BMC. Now this is prior to any OS code, any of the host code running. This is early in BIOS. Once it sends that KCS nonce over to the BMC, then instead of reconfiguring the whole thing every time, anytime that SMM would want to send one of these admittedly rare events for some hardware failure, it'll unlock this feature while it's in SMM by sending that KCS nonce back to the BMC again. The BMC would acknowledge it, turn the KCS, or at least not turn it on, but set a flag saying that yes, we're now allowing any traffic on this bus to this endpoint. They would send the normal KCS, perform the normal KCS message, and then clear the KCS nonce again to ensure that returning from SMM back to the host would leave it in a state where anyone running on the host or any code running on the host couldn't access this feature. I think we'll skip this one and go to the end. But yeah, do you want to jump on?
Yeah, sure. Yeah, and the case study that we skipped over is really some of the same story, right? So it's a Flash component that's exposed over an interface that it should not have been, and then they realized that, and so they tried to put a lock on it. In that particular case, the lock didn't really work, and so there were some CVEs for it a little while ago. And now as I understand it, like the solution was to just remove the door entirely. So like now, like where it used to be open all the time, and if you knew the key, but then the key didn't really work right, and rather than re-engineer all that, it's all shut off except for like that small window during boot. So, okay, so wrapping up, what's interesting? What do we care about? What's interesting to look at in the future? You mentioned some of this at the beginning, so just kind of talk through it again, right? That attack chains in really restrictive environments are the most interesting. They're the ones who turn on all the security features, right? They're the ones who care about security enough to have actually done those things. And the attack surface that's left over is still there, and it's the sort of the current hardest part that you've got to deal with, right? So that's interesting. The peripherals, like as I mentioned earlier, it's not well understood yet, right? Pivoting back to the host is something that I think is probably very well understood in certain quiet corners of the world that don't talk about it. Publicly, there's actually not a whole lot. There's a very interesting attack surface from BMCs in particular. Like there's a lot of emulated devices that get exposed up to the host that, it's sort of like it's like plugging a face dancer into the host or something. Like it's like hardware types of attacks that you would normally think of, like I'm going to walk up to this machine and plug this thing in and compromise it that way, but you're doing it through the BMC remotely. And then the userland stuff at the end, I think it needs a lot more focus. It needs, it's got all of those same problems that I talked about earlier. Some of them in crazy cases are even exposed out onto the network. So you end up where, like, perhaps I can flash your firmware across the network. Like that should be a well-defined interface that's locked out appropriately, right? That you're doing that on purpose and you're not exposing it on accident. Right, so last thoughts?
Yeah, so these are hopefully our takeaways. despite all this hardening, the attack surface remains on modern servers. We talked through a bunch of the hardening. We talked through some of the ways we're trying to defend against it. But it's such a complex system, and it's such a legacy system that there's always these dark corners that have been forgotten about for 15 years. And I've always worked that way, but can no longer work that way securely and reliably. The second takeaway is that SMM is not a secure enclave, right? We've seen attacks, microarchitectural attacks against it. We've seen it has all of the problems that you would imagine when you're pretending that it is a separate processor, but it isn't, right? It's running on the same chip as a CPU. Additionally, we have a lot of hardening that go against it, but all that hardening is hardening, approaching it not as a TPM, not as a secure enclave. So things like SMRAM read vulnerabilities are going to have a huge impact that they wouldn't have on another system that was looking at this as holding secrets. And then again, we're really hot on this idea of coming into a peripheral and then coming back out of it. So persisting on a peripheral and then looking at all the attack surface that you've gained there. So the idea again of this map of using this idea of searching for attack surface and then continuing iterating on that. So once you have a foothold on something like a hard drive or a SATA controller, now what happens next? Can you reinfect the host? Can you, what other SM buses do you have access to? All these things are really interesting to us.
And we're out of time. So thank you. We're gonna, if you have any questions, grab us as we're walking out, or we're walking on our way over to the, what's it called? The wrap room. Yeah, let's come say hi. Thank you. Thanks a lot.